Hello everyone. Today I am going to start with linear differential equations. How to know whether the given equation is linear or non-linear. So basically a differential equation is said to be linear if it satisfies the two conditions. The first is the dependent variable and all its derivatives occur only in first degree, and the second condition is there is no term containing the product of dependent variable and its derivatives. So this is the general form of the linear differential equation. Here a naught dny over dx and a1 dn minus 1y over dx and minus 1 up to a and y is equal to x. These a naught, a1, a2 up to an, these may be constants or some function of x. This right hand side capital X, this may be any function of the x. So clearly from this general form, we can see that this is satisfying both the conditions, that the dependent variable and all its derivatives of any order, they all are occurring in degree 1, and the second condition is also satisfying. There is no term which is containing the product of dependent variable and its derivative. So this fulfills both the conditions of linear differential equation. This is the general form of linear differential equation. So now we see that the degree of linear differential equation is 1 and it may have any order. So here we will discuss first order linear differential equations. That means the linear differential equations which are having only first order. So these equations are of the form dy by dx plus py is equal to q. Here p and q, these are functions of x or they may be some constants. So the general solution of this type of differential equations is obtained by multiplying this equation with a factor. That factor is known as integrating factor. Integrating factor. So what happens when we multiply this equation with the integrating factor, say e raised to power integration p dx, what happens? The left hand side becomes exact derivative of some functions. So after getting the exact derivative, what we can do? We can integrate both sides and we can easily obtain its solution. So you can see here, if I multiply this equation with this integrating factor on both sides, then I am getting this one. After solving this, it is, sorry, this is not y, this is actually x. Okay, so then dy dx plus p integrating factor y is equal to e integration p dx q. So now we can see this left hand side, it is becoming exact derivative of, and this one y. So if you use product rule of differentiation, you can see that this becomes exact derivative of this function y into e raised to power p dx. So now we get exact derivative. So after doing integration on both the sides, we get y and then integration of this term plus constant of integration. So this becomes the general solution of this type of first order linear differential equation. So in short, we can write the general solution of first order linear differential equation is given by, in short, we can write it as, this is nothing, this is just the integrating factor. So y multiplied with integrating factor is equal to integration of, here this is q multiplied again with integrating factor. So here we are integrating with respect to x, so we can write dx. Okay, so because we are integrating with respect to x, okay. So plus constant of integration. So this represents the general solution of this first order linear differential equation. So here in this linear differential equation, x is the independent variable and y is the dependent variable. We can express the same thing by taking x as dependent variable and y as independent variable. So dx dy plus px is equal to q. It may be known as another form of linear differential equation of first order of first order. Okay, so this another form. This here x is the dependent variable and y is the independent variable. So clearly p and q, they will be the function of y, or they may be some constants. So by using the same approach as we have used previously, we can get its integrating factor, that would be e raised to power integration p dy p dy, and its general solution would be given by the formula x multiplied with integrating factor is equal to integration q multiplied with integrating factor dy. So this would be the general solution of this type of linear differential equation of first order. So these are the two forms of first order linear differential equation. This is the first one and this is the second one. So now we come to the equations which are known as reducible to linear differential equation. So what does it mean? It means that there are some differential equations which are not linear in their current form, but they could be converted into linear differential equation. So by using some suitable substitutions, so this type of equations have a specific name. They are known as Bernoulli's equations. Bernoulli's differential equations. Okay, basically these are those equations which can be reduced into linear differential form. So their general form looks like dy by dx plus py is equal to q y raised to power n. So now if we compare it with the general form of linear differential equation, we can easily see that this y raised to power n, this is just disturbing the linear differential equation form, otherwise rest of the things are fine. So in order to get rid of this y raised to power n, what we do, we divide the whole equation with y raised to power n. Then we get this one. This is n minus 1. You can say p is equal to q. So now by making some suitable substitution in this equation, what we can do, we can convert it into linear differential equation. So the substitutions are let y raised to power n minus, here we are having, this is okay. So what we can do, we can substitute 1 upon y raised to power n minus 1 as you can say t. Okay, fine. So that means y raised to power 1 minus n, we can say this is t. So after doing differentiation on both the sides, we get dy by dx, that would be equal to dt by dx. So here that means we can write 1 upon yn dy by dx, that would be 1 upon this and dt by dx. So now we can put these two substitutions back in the Bernoulli's differential equation here. So what we get 1 upon 1 minus n dt by dx plus 1 minus n p, and here it is t, is equal to 1 minus n into q. So if we assume this 1 minus n into p as p dash and this 1 minus n q as q dash, what we get? We get here, this is okay. So I think here after doing this substitution, we are getting this one. This is 1 by n, 1 minus n, okay. This 1 by y raised to power n minus 1, that is t. Okay, so so what we are getting? We are getting this one. Okay, so here by using these substitutions, what we get? We get dt by dx plus p dash t is equal to q dash. Okay, where p dash is 1 minus n into p and q dash is 1 minus n into q. So now you can see that this is the standard form of linear differential equation of first order. And we know that we are having the standard procedure to find out its solution. So by taking that standard solution procedure, we can find the general solution of this Bernoulli's equation. So no need to cram all these things that what we have to do here. Just you have to do simple things. You have to divide the Bernoulli's equations, and after that you just need to make the substitutions. After putting the substitutions back, you will get the linear differential equation, and then by using the standard procedure, what you can do is you can find the solution of that one. Okay, so let's take a couple of examples to solve linear differential equations of first order. So for example, the first question is, we have to solve, say, okay, you can say dy by dx plus y by x is equal to x raised to power 2. Okay, so clearly this is the linear differential equation, as all the dependent derivative and their differential coefficients, they are in first degree. There is no term containing the product of y and its derivative. So on comparing this with the standard form of linear differential equation, that is dy by dx plus py is equal to q, we can get p as 1 by x and q as x raised to power 2. So we know by the standard solution process that integrating factor of these linear differential equation is given by the formula e raised to power p dx. Then using that formula, it will become 1 by x dx, and after doing the integration, e log x, and we know it would be x now. So integrating factor is coming out to be x. So now we can directly use the solution formula. The solution is given by, I hope you remember, the formula was y into integrating factor is equal to integration q into integrating factor dx plus constant of integration. So here integrating factor is this, q is having a value x square. So we are getting this one. So this is y into x. So integration of x raised to power 3 is x4 by 4. So this is the required solution, general solution of this given differential equation. So it will be your answer. Okay, so this one. Okay, so let's take one more example, that how to solve linear differential equation. Okay, so let's take the second one as, you can say you have to solve, say, x plus 2 y cube dy by dx, say is equal to y. Okay, so let's first find out this is of which form. So what we can do, from the given equation we can write it as, okay, so That means dx over dy, that would be x plus 2y cube upon y. So we can say, okay, so that means here we are having the second form of linear differential equation where x is the dependent variable and y is the independent variable. Okay, so that means it would be the case of this one. Okay, so clearly we can compare it with the general form of linear differential equation dx over dy plus px is equal to q. So on comparing, we are getting p as minus 1 by y and q as 2y square. So we know its integrating factor is given by the formula e raised to power pgy. So by using that formula, integrating factor would be e raised to power minus 1 by y dy. We know that its integration is log y. So that means it is 1 by y. So this is the value of integrating factor here for this particular differential equation. So now we can use the formula for general solution is x multiplied with integrating factor is equal to q multiplied with integrating factor dy plus constant of integration. So that is x 1 by y. Value of q is 2y square and this is 1 by y dy. So after doing the integration, okay, so this is 2y dy. So integration of this is 2y square by 2. So x y square plus c, or we can say x is equal to y cube plus cy. That would be the general solution of this differential equation. Okay, so in this way we can check the linear differential equation is of which form, and we can apply the corresponding standard formula to solve to find the solution of the given differential equation. Okay, so let's take one more example. So now suppose we have to solve the differential equation dy by dx plus xy is equal to xy square. Okay, so now let's find out this is of which form. Okay, so yeah, this is Bernoulli's equation. Okay, this is directly not in a linear differential equation form because of the presence of this y square. So if we want to convert it in linear differential form, what we have to do, we have to multiply the given equation with this y raised to power 2. After multiplying this, we are getting this one. Okay, so now we know in Bernoulli's equation, we have to make a suitable substitution in order to convert it into linear form. So let the solution, the substitution would be say 1 by y is equal to t. So on differentiating both the sides, we are getting minus 1 by y square dy by dx as dt by dx. Okay, so after putting these two substitutions back here in the equation, we are getting minus dt by dx plus this is 1 by y is t, so this is x. So now this becomes linear differential equation. Okay, so now what we can do, so yes, this becomes the linear differential equation. So now we are having two methods to solve it. Okay, either we can use the variable separable method here, or we can solve it by the standard procedure of linear differential equation. So you can do it any way you like. So okay, let me try it with variable separable method. So here dt by dx, it could be x minus xt, or we can say that is 1 minus t, because here in this question variable separable technique is also possible. So I am making use of that. So it would be 1 minus t, or here this is x dx. Okay, so because of this minus, so Okay, so we forget to take this negative sign. So what we can do here, if we are removing this negative sign, so if we are removing this negative sign here, so we can do, okay. So this is this one. So here it would be, okay, let me correct this. So it would be now just, this is x plus xt. Okay, so if we are removing this one here, it would be minus. So this is minus. So okay, let me correct it. So it would be x t minus 1. Okay, so here rather than 1 minus t, this is, okay, t minus 1, and here it is x dx. So now variables are separated. On left hand side we are getting all t and dt, and on right hand side we are getting x and dx. So now just doing the integration on both the sides, we get, this is log t minus 1, and here this is x raised to power 2 by 2 and plus constant of integration. So now we can put our t back. Our t was having a value 1 by y, so using that one we are having 1 by y minus 1, that is x raised to power 2 by c. So this is the general solution of this Bernoulli's differential equation. Okay, so this is all about linear differential equation. So